Today's class we look at 3-dimensional elastic problems. So far we have looked at planar and axisymmetric elastic problems, which are a special case of these 3-dimensional elastic problems. If you recall, the plane stress plane strain problems that we looked at are special case of 3-dimensional elastic problems, and also axisymmetric problems that we looked at is also a special case of 3-dimensional elastic problem. Only thing is, when structure, loading and material properties satisfy certain criteria, we can model a 3-dimensional elastic problem as a 2-dimensional one. If it is plane stress plane strain case, we have 3 stress components and 3 strain components that we actually computed at each element after solving for displacements, whereas if you look at axisymmetric elastic problems, we computed actually 4 components of stresses and strains in each element or at each integration point. So, in plane stress plane strain problems, the constitutive matrix is of dimension 3 by 3. In axisymmetric elastic problems, the constitutive matrix is of dimension 4 by 4. When the structure, loading and material properties do not permit us to make any of these assumptions of plane stress plane strain or axisymmetric case, then we need to model the entire 3-dimensional problem using finite element method. In that case, we are going to have 6 components of stresses and 6 components of strain, and the constitutive matrix which relates stresses with strains is going to be 6 by 6. And also, if you recall, for plane stress plane strain problems or axisymmetric elastic problems, at each point there are 2 degrees of freedom. If it is plane stress plane strain problem, it is in the x direction and y direction. If it is axisymmetric elastic problems, it is in the radial direction, axial direction, 2 displacement components, whereas for 3-dimensional elastic problems we are going to have 3 displacement components, one in the x direction, another in the y direction, the third one in the z direction. So, now let us look at 3-dimensional elastic problems. Planar and axisymmetric elastic problems considered in the previous lectures are special cases of general 3-dimensional elastic theory. The general case of 3-dimensional stress analysis shall be discussed in the next few lectures. A 3-dimensional elastic problem involves 6 stress components: sigma x, sigma y, sigma z, tau x z, tau y z, tau x y, where the first 3 components, that is sigma x, sigma y, sigma z, are normal stresses, and tau x z, tau y z, tau x y are shear stresses. And corresponding to these stresses, there are 6 strain components, and the primary unknowns are 3 displacement components along 3 coordinate directions, that is along x direction, which is denoted with letter u, along y direction, which is denoted with letter v, along z direction, which is denoted with letter w. So, these are the 3 displacement components u, v and w, and there are 6 stress components, and all these 6 stress components can be put together in a vector denoted with sigma as shown here, and strain vector consists of 6 strain components. All the 6 components of strain can be put together in a vector denoted with letters epsilon in this manner. And now we need to know how these strains are related to displacements. As we already looked at for planar and axisymmetric elasticity problems, under small displacements and strain assumptions, strain displacement relations for 3-dimensional elasticity problems can be written like this, that is epsilon x is partial derivative of u with respect to x, epsilon y is partial derivative of v with respect to y, epsilon z is partial derivative of w with respect to z, gamma xy is partial derivative of u with respect to y plus partial derivative of v with respect to x, gamma yz is partial derivative of v with respect to z plus partial derivative of w with respect to y, gamma zx is partial derivative of w with respect to x plus partial derivative of u with respect to z, and assuming linear elastic behavior, the stresses and strains are related through this equation sigma is equal to c times epsilon, where c is the constitutive matrix, which is going to be of dimension 6 by 6, since there are 6 stress components and 6 strain components. For isotropic material, isotropic linear elastic material, this constitutive matrix is given by this one, where E is Young's modulus, mu is Poisson's ratio, mu is Poisson's ratio. So, constitutive matrix require 2 material parameters, Young's modulus and Poisson's ratio. To derive finite element equations, we require potential energy functional. The finite element equations for 3-dimensional elastic problems can be derived using potential energy functional. This potential energy functional can be written as follows. Potential energy functional is denoted with letter pi. Pi is equal to u minus ws, where u is strain energy and ws is work done by the applied forces. This potential energy functional is going to be a function of all the 3 displacement components, that is u, v and w. And this is similar to plane stress, plane strain problems or axisymmetric elastic problems that we already looked at, except that potential energy functional, there is function of only displacement component along 2 directions. So, now let us look at how strain energy looks like. Strain energy can be calculated by evaluating this volume integral half volume integral epsilon transpose sigma, substituting epsilon is equal to c times, or sigma is equal to c times epsilon. This can be further written as half volume integral epsilon transpose c epsilon. Please note that this formula can be used only under linear elastic assumptions or small displacements and strain assumptions. Now, work done by the applied forces. Work done by the applied forces is given by components of traction along x, y, z directions multiplied by the corresponding displacements and evaluated over the surface over which traction components are applied. So, work done by the applied forces is given by this surface integral, and if the specified concentrated forces or body forces are present, work done by these forces can be calculated in a similar manner. So, we looked at how to evaluate strain energy and also how to evaluate work done by the applied forces. So, we are ready to formulate, or we are ready to derive finite element equations for 3 dimensional elastic problem. Before that, we need to make a choice of the type of element that we are going to use for solving 3 dimensional elastic problem. Here basically as a part of this 3 dimensional elastic problems, we are going to look at 4 node tetrahedral element, which is basically a linear element for solving 3 dimensional elastic problems, and also we look at 8 node linear solid element, commonly known as brick element, and 20 node solid element with curved edges. So, in this lecture, let us start with 4 node tetrahedral element. A typical element is shown here. 4 node tetrahedral element. At each node there are 3 degrees of freedom, displacement component along x direction, y direction, z direction. Total there are 4 nodes. This is the simplest element that we can have for solving 3 dimensional problems. This element is going to be linear along x direction, y direction, z direction. So, it is counterpart of 3 node triangular element, which is a linear element for solving 2 dimensional problems, similar to 3 node triangular element, which we usually call it as CST, constant strain triangular element. Similarly, 4 node tetrahedral element is a constant strain element in 3 dimensions. So, it is convenient to use isoparametric mapping concept to develop finite element equations in a manner similar to that we already used for triangular elements for 2 dimensional case. So, we need to map this actual element onto a parent element like this. Parent element is shown on the right hand side. The nodal coordinates of all the 4 nodes of parent element are indicated in the figure. Node 1 is located at 1 0 0, node 2 is located at 0 1 0, node 3 is located at 0 0 1, node 4 is located at the origin 0 0 0 in RST coordinate system. So, actual element is going to be mapped onto this parent element when we are deriving element equations. So, this 4 node tetrahedral element is an extension of linear triangular element, which we already looked at for 2 dimensional problems to 3 dimensions, extension of triangular element to 3 dimensions. So, the finite element formulations follows very closely the development of triangular elements. However, this element is not that popular because of difficulty in dividing 3-dimensional domain into tetrahedra, and also main advantage of this element is its simplicity in its formulation. So, now let us look at how to derive shape functions for this 4 node tetrahedral element, and the procedure that we are going to adopt is similar to that we already adopted for 2-dimensional problems like triangular elements in case of 2 dimensions. So, we start with a polynomial having number of coefficients equal to the number of nodes of the particular element, and by substituting the trial solution values at the nodes, we solve for the coefficients and substitute back these coefficients into the trial solution and group terms having similar coefficients which corresponds to the nodal values, and then we are going to arrive at finite element shape functions. The governing equations for 3-dimensional elastic problems involve u, v, w, which are displacements along x, y, z directions. 3 different trial solutions are therefore required. There are 3 unknown displacements at each node, 3 degrees of freedom per node. So, trial solution, there are 4 nodes. So, linear trial solution in 3 dimensions, u is equal to alpha 1 plus alpha 2 x plus alpha 2 alpha 1 plus alpha 2 x plus alpha 3 y plus alpha 4 z. Similarly, v is equal to beta 1 plus beta 2 x plus beta 3 y plus beta 4 z. W is equal to gamma 1 plus gamma 2 x plus gamma 3 y plus gamma 4 z, where these alphas, betas and gammas are unknown solution parameters, and these solution parameters must be expressed in terms of finite element shape functions before proceeding any further. So, what we will do is we will adopt procedure that we are already familiar with. For the parent element, the shape functions can be derived very easily as follows. You start with the trial solution, substitute the nodal value of the trial solution corresponding to node 4, substitute r is equal to 0, s is equal to 0, t is equal to 0, and equate the trial solution value to the trial solution value to the value of the displacement or the value of the nodal value at node 4. Similarly, trial solution evaluated at node 1 is equal to u1. Applying that condition, we are going to get the second equation in terms of alpha 2, and similarly applying the condition that trial solution evaluated at node 2 is going to be u2, we are going to get the third equation, and similarly we get the fourth equation by applying the condition that trial solution value evaluated at node 3 is equal to u3. So, finally, we got 4 equations in terms of alpha 1, alpha 2, alpha 3, alpha 4, and substituting back this alpha 1, alpha 2, alpha 3, alpha 4 values into the trial solution, we get this, which can be written in a matrix and vector form as shown on the right hand side of the given equation. So, shear function corresponding to node 1 is R, shear function corresponding to node 2 is S, shear function corresponding to node 3 is T, and shear function corresponding to node 4 is 1 minus R minus S minus T. So, this is how we can arrive at the shear functions for 4 node tetrahedral element. Basically, the procedure is similar to that we already adopted for deriving shear functions for 3 node triangular element, except now the dimension is increased. So, we can also solve starting with u and w, since same trial solution is used for u and w, v and w. Also complete shear function matrix for the parent element can be written as follows: u expressed in terms of finite element shear functions, v in terms of finite element shear functions, w expressed in terms of finite element shear functions. Putting together all these things in a matrix and vector form, we can write like this, where n transpose is a matrix comprising of finite element shear functions of all the 4 nodes of this tetrahedral element, and D is the vector consisting of nodal displacements, all the 3 components of displacements at each node for all the 4 nodes. So, the derivatives of u, v, w with respect to r, s, t can be obtained by direct differentiation of shape functions. Please note that n1 is equal to r, n2 is equal to s, n3 is equal to t, n4 is equal to 1 minus r minus s minus t. So, we can easily calculate what is the derivative of this n1, n2, n3, n4 with respect to r, s, t. So, derivatives of u, v, w with respect to r, s, t can be easily obtained once we know the derivatives of shape function with respect to r, s, t, which we can easily get, since we already know the expressions for shape functions. So, for examples, derivative of u can be evaluated as follows: partial derivative of u with respect to r, partial derivative of u with respect to s, partial derivative of u with respect to t can be written in a matrix and vector form like this. If you put together all the partial derivatives of u with respect to r, s, t in a vector as shown there. So, taking partial derivatives of shape function with respect to r, s, t, it can be easily checked that in fact partial derivatives of u with respect to r, s, t is given by this one. Similarly, derivatives of u, similarly derivatives of v and w with respect to r, s, t can be derived. So, this is how derivatives of displacement components with respect to r, s, t can be obtained. But if you recall, strain is related to derivatives of displacement components with respect to x, y, z. So, we need to know what is the relationship between x, y, z coordinates and r, s, t before we start expressing strains in terms of finite element shape functions and displacements. So, to know the relations between r, s, t and x, y, z, we can use isoparametric mapping concept. Based on that, x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4, substituting n1, n2, n3, n4, that is n1 is equal to r, n2 is equal to s, n3 is equal to t, n4 is equal to 1 minus r minus s minus t. Substituting that information, this expression can further be simplified as shown on the right hand side, where x14 means x1 minus x4, x24 denotes x2 minus x4, x34 denotes x3 minus x4. Similarly, we can write a y in terms of RST, where xi xj has the meaning xi minus xj, yij has meaning yi minus yj. So, similarly, we can also write z, or we can also express z in terms of RST using finite element shape functions of this 4 node tetrahedral element. And when we do that, we get this. So, now we know how to express x, y, z in terms of RST. So, we can easily take what is partial derivative of x with respect to RST, y with respect to RST, z with respect to RST, and we already know how to calculate derivatives of displacement components with respect to RST. So, we using both these informations and using chain rule of differentiation, we can easily arrive at derivatives of displacement components with respect to x, y, z. Once we know derivatives of displacements with respect to RST, and finally we can write the strain displacement relations in relationship in terms of finite element shape functions and the nodal displacement components at the nodes. So, strain displacement relationship, partial derivatives of u, v, w are evaluated using chain rule. Here derivatives of u alone are shown, partial derivative of u with respect to r can be written as partial derivative of u with respect to x times partial derivative of x with respect to r plus partial derivative of u with respect to y times partial derivative of y with respect to r plus partial derivative of u with respect to z times partial derivative of z with respect to r. Similarly, we can write partial derivative of u with respect to s, partial derivative of u with respect to t. These three equations can be put together in a matrix and vector form. Writing three equations in a matrix form, we get this relation, where j is used to denote partial derivatives of x with respect to RST, where j is used to denote components of partial derivative of x with respect to RST, y with respect to RST, z with respect to RST, or a matrix consisting of partial derivatives of x with respect to RST, y with respect to RST, z with respect to RST is denoted with letter j, which is called Jacobian matrix. So, this relation this equation basically helps us to calculate partial derivatives of displacement component along x direction with respect to RST once we know its derivative with respect to x, y, z. If we want the inverse relation, that is, if we want to know how to calculate partial derivatives of displacement component u along x, y, z directions, once we know its partial derivatives with respect to RST, we need to know what is j inverse. Derivatives of u with respect to x, y, z can be computed by inverting J matrix. So, the inverse relation is like this. Since we already know x in terms of RST, y in terms of RST, z in terms of RST, we can easily take partial derivatives and express Jacobian matrix in terms of x y z coordinates. Similarly, once we express Jacobian matrix in terms of x y z coordinates of all the 4 nodes, we can easily find what is J inverse. So, taking derivatives of the relations that we derived based on isoparametric mapping, these are the 3 equations that we derived based on isoparametric mapping. Taking partial derivatives of these with respect to RST, we can easily check that Jacobian matrix is indeed given by this, where x 1 4 2 4 3 4, y 1 4 2 4 3 4, z 1 4 2 4 3 4 has meaning that we already discussed earlier, that is x I j is nothing but x I minus x j, y I j is y I minus y j, z I j is z I minus z j. So, using or with that understanding, we can easily, once we know all the coordinates of all the 4 nodes of this tetrahedral element, we can easily calculate what is j numerical value. Once we have numerical value of j, we can easily find what is j inverse. So, j is given by this, which is a 3 by 3 matrix. So, we can easily find what is j inverse analytically in this manner. So, once we know the nodal coordinates of all the 4 nodes of tetrahedral element, we can easily plug in that into this equation and get what is j inverse. And here determinant of j is given by this equation. If you recall, determinant of j has some importance. For a valid isoparametric mapping, determinant of j should be non-zero over the entire element domain. Here we are dealing with 4 node tetrahedral element. So, element domain goes from RST going from 0 to 1. So, the isoparametric mapping is valid as long as the determinant of j is non-zero over the domain RST between 0 and 1, entire domain of parent element. So, we are ready to express derivatives of displacement components with respect to x, y, z in terms of nodal values. This equation gives the relationship between partial derivatives of u with respect to x, y, z, and substituting all the information that we just derived, we arrived at this equation which relates partial derivative of u with respect to x, y, z with the nodal displacement components of all the 4 nodes of this tetrahedral element, and plug in the components of j inverse, and simplifying we get this equation. Similarly, we can derive equations for partial derivatives of v with respect to x, y, z, partial derivatives of w with respect to x, y, z, and they look like this. So, now we are ready to express strains in terms of nodal displacements. Strains now can be expressed in terms of nodal displacements by choosing appropriate rows from the above matrices. Since strain components are defined like this, so putting together all the strain components, the corresponding definitions, that is epsilon x is equal to partial derivative of u with respect to x, epsilon y is equal to partial derivative of v with respect to y, epsilon z is equal to partial derivative of w with respect to z, gamma xy is partial derivative of u with respect to y plus partial derivative of v with respect to x, and so on, putting together all that information. And substituting the partial derivatives of displacements with respect to x, y, z, we get the right hand side, which relates strains with nodal displacements and which can be compactly written as epsilon is equal to b transpose t. And here H1, H2, H3 are defined, and these H1, H2, H3 are basically they are related to the components of inverse of Jacobian through these equations. If you see this strain displacement relations, it can be easily verified that all terms in the B matrix are constant. So, this element is constant strain triangular element, just like 3 node triangular element for plane stress plane strain problems. So, we express strains in terms of displacements, nodal displacements. So, now we are ready to derive element stiffness matrix. For that we need to go back to the strain energy definition. Strain energy can be written or can be expressed through this equation, substituting epsilon is equal to b transpose d, that information into this equation. We can evaluate strain energy through finite element approximation as half d transpose kd, where k is element stiffness matrix and it is given by this integral, volume integral b c b transpose. Since b is constant and since constitutive matrix is also constant, we can pull them out of the integral. Finally, k is given by b c b transpose times v. V is nothing but volume of tetrahedral element. If you recall, when we are deriving finite element equations for 3 node triangular element, area of triangle is related to determinant of j, area of triangle or determinant of j is twice the area of triangle. Similarly, determinant of j here for 4 node tetrahedral element is 6 times volume of the tetrahedral element, or volume is given by 1 over 6 determinant of j. Substituting that, we can evaluate element stiffness matrix using this equation. Please note that here the assumption or this integral is simplified in this manner based on the condition that b is constant. If b is not constant, we need to do numerical integration, we need to adopt some kind of numerical integration like Gaussian quadrature, where is the volume of element, and it can be easily shown that volume of element is 1/6 of determinant of j. So, this is how one can evaluate element stiffness matrix for 4 node tetrahedral element. So, we are ready, except that we do not know what is force vector. So, now let us look at equivalent force vector. Equivalent nodal forces, let Tx, Ty, Tz be the components of traction applied in x, y, z directions. So, work done is given by this displacement components times traction components integrated over the surface over which tractions are specified, and substituting displacements in terms of finite element shear functions, displacements u, v, w in terms of finite element shear functions and nodal values, we get what is given on the right hand side of this equation, which can be further simplified as d transpose qt, where q is the equivalent nodal load vector defined as surface integral matrix consisting of finite element shape functions times the components of tractions. So, to evaluate this qt, integration can be performed in a closed form if specified surface tractions are assumed to be constant over the element, and this is for one phase of the tetrahedral element, and similar integrations needs to be performed separately for forces applied along different faces of tetrahedral elements. And these integrations are similar to the integrations for body forces in case of triangular elements. So, substituting n matrix comprising of finite element shear functions of all the 4 nodes of this tetrahedral element and simplifying, we get this qt on one of the face joining nodes 1, 2, 3. That is the reason why q and subscript t phase 1, 2, 3 is shown there. It is given by area of phase 1, 2, 3 divided by 3 times the components or a vector consisting of components of tractions that are applied. It can easily be noticed, since we are dealing with phase joining nodes 1, 2, 3. If you see this vector, it is having non-zero components corresponding to nodes 1, 2, 3 and 0 components corresponding to node 4. And also it can be noticed that the total load on the phase 1, 2, 3 is divided equally among all the 3 nodes defining that phase. And again this equivalent nodal load vector is based on the condition that Tx, Ty, Tz are constant. If they are not constant, then we need to do numerical integration of previous equation, assuming Tx, Ty, Tz as functions of spatial coordinates. And similar expressions can be written for forces applied on other faces. It should be noted that qt vector implies that total load on face is divided equally among the 3 nodes defining that face. And body forces can be handled in a similar manner. So, we looked at how to evaluate equivalent nodal force vectors for the applied tractions, traction components along any of the faces, and we know how to evaluate element stiffness matrix. So, we can easily assemble element stiffness matrix and equivalent nodal load vector given a discretization. And once we evaluate these quantities, that is element stiffness matrix and equivalent nodal load vector for each of the elements, we need to assemble global stiffness matrix and global force vector based following similar procedure that we followed for 2-dimensional problems based on the element connectivity. We can easily put the contribution from each of the element in the corresponding locations in the global stiffness matrix and get the global stiffness matrix and also global nodal force vector, and applying appropriate essential boundary conditions, and if the essential boundary condition turns out to be 0, we can delete that particular row and column of the global stiffness matrix and arrive at the reduced equation system, which we can solve for the nodal displacements. And all this procedure is similar to that we already looked at for 2-dimensional problems. Once we get the nodal displacements, we can calculate strains through strain displacement relations, and once we arrive at strains, we can calculate stresses through stress strain relation. The stresses that we are going to obtain are going to be in terms of x, y, z coordinates, that is sigma x, sigma y, sigma z. To know whether a particular structural component or mechanical component satisfies certain failure criteria or not, we need to know what are called principal stresses, which are different from sigma x, sigma y, sigma z, and all these shear components, that is tau x y, tau y z, tau z x. So, now let us look at how to calculate these principal stresses. For 3-dimensional elastic problems, the normal and shear stresses can be combined into principal stresses, which can be used for further applications in any of the failure criteria. So, these principal stresses are going to be the roots of the following cubic equation, which is actually in terms of stress invariants, I1, I2, I3 are called stress invariants. Where I1 is defined like this, I2, I3. So, once we know all the components of the stresses at a particular point, we can easily evaluate what is I1, I2, I3 using the shear normal stress components and shear stress components. Once we get the numerical values of I1, I2, I3, we can solve these cubic equations for the 3 roots. That gives us sigma 1, sigma 2, sigma 3, which corresponds to the 3 roots of the cubic equations that is shown here. Or analytically, the roots of that cubic equation can be expressed as follows. Sigma 1 is given by I1 over 3 plus c times cos theta, sigma 2 is given by I1 over 3 plus c times cos theta plus 2 pi over 3, I3 is given by I1 over 3 plus c times cos theta plus 4 pi over 3, where theta is defined like this, 1/3 cos inverse minus of 3b over AC, where A, B, C are defined like this. In terms of stress invariants, so either we can evaluate sigma 1, sigma 2, sigma 3 by solving the cubic equation, which is in terms of stress invariants numerically, or we can use these analytical solutions to get sigma 1, sigma 2, sigma 3 for further application in any of the failure criteria.